We're going to continue on with our discussion of binary trees, and today we're going to look at a specialized type of binary tree called a binary search tree and some of the special properties of that. So, searching a general tree, you can use any form of tree traversal, in order, post order, or pre-order traversal, but in some cases that can be a little bit slow. In the worst case scenario, it's like performing sequential search on a linked list, which is an O of N algorithm. And in particular, in this tree, finding 53 may prove to take a few more operations than finding something like 78. So, it depends on what you're looking for as to how quickly you can actually find it. So, a better structure will enable us to find things more quickly. And in this binary tree, data in each node is larger than in the left child and smaller than the right child. So all the things in the left are smaller than the root, and all the things in the right are larger than the root. Again, we can go with a recursive definition of a tree, and here a binary search tree is either empty or it has these properties. It has a root node, has two sets of nodes, a left subtree and a right subtree, and the key in the root is larger than every key in the left and smaller than every key in the right subtree. And left tree and right tree are both binary search trees, so this is a recursive definition. Some of the things you can do, you can determine if it's empty. That's fairly easy. If root is equal to null, then it's an empty binary search tree. Searching for a particular item, which is kind of what we're going to focus on. Insertion or deletion, we'll cover that as well. The height of the tree is a recursive function, number of nodes and leaves in the tree, traversing and copying. So for searching binary trees, we want to start at the root node if there's no match. So check and see, hey, is the root the thing we're looking for? If it's no match, then and the search item is smaller than the root node, we go left. Otherwise, we go right. And we continue these steps until the search item is found or it ends at an empty subtree. This should seem pretty familiar, and it's a lot like binary search. In fact, it's pretty much binary search. So the performance of the search depends on the shape of the tree. In the worst case scenario, where we pick the smallest item to be the root and everything lands in the right subtree as an A, or we pick the largest to be the root and everything goes in descending order like B, it's going to be like sequential search, and so it's O of N. But in most cases, you have a better structured tree. So with a better structured tree, you end up with O of log N comparisons, just like binary search. And the average number of nodes visited in a search of a binary search tree is 1.39 times log 2 of N. So that's O of log N. And the number of key comparisons is approximately 2.77 log to the base 2 of N. So that's O of log N. So both of those are O of log N. So it's a very, very fast algorithm in the standard case. Worst case scenario, you do get sequential search, but in general, most trees won't be structured that way. So one other thing we probably need to do is insertion. We need to add things into our tree from time to time, and this is a little bit trickier than just putting them anywhere in the tree or at the first open place in the tree. We need to put them in the place where they belong. So when we want to insert an item, we need to make sure the resulting tree is still a binary search tree. So we need to find a location where it'll need to be placed that's similar to the search function. So if it's smaller than the root, then we're going to go left and look for it. If it's larger than the root, we need to go to the right. And here we need to keep two pointers. One is the current and the other is the parent of the current in order to insert. We also make a rule that we can't have duplicates, so we need to end an empty subtree. Deletion, that's even a little bit trickier, and it depends on the case. So there are 4 cases. One, you want to delete a leaf or something that's the furthest down the tree. The other one is if you want to delete something that has no subtree, something that has no right subtree, and finally it's got both a left and right subtree. And that one's probably the trickiest, but let's see how we can go about doing this. So we'll start with a leaf. That's the easiest one. Here we have a binary search tree, and we have 45 down at the very bottom. That's a leaf. It doesn't have any children. So we search the tree and we arrive at 45. Because it's a leaf, we can just update the parent to have its left link point to null, and we deallocate the memory. So just use a nice deletion operation, and away we go. Case number 2 is, so this is what case number 1 looks like. We just update 48 to have a null left subtree, and we delete 45. And there's our updated tree. Case number 2 is a bit trickier. We don't have a left subtree. So here, take a look at 30. It's over on the left of this diagram. 30 has no left subtree. So what we want to do is we want to make the parent of 50 point to 30's right child. So we make 50 point to 35. And then that points to the right subtree of 30, and we can go ahead and delete 30, and that ends up promoting 35 and moving its subtree up when we look at that structure. So again, we take 50, have it point to, that's why we maintain the 2 pointers, have it point to the right subtree of 30, and voila, 35 gets moved up along with its subtree. Case number 3 is there's no right subtree. So suppose we want to delete 80. 80 is over on the right-hand side, about 2 down, 60, 70, 80. 80 doesn't have a right child. So what we want to do is make the right link of the parent of 80 point to the left child of 80. So again, we take 70 and have it point at 75, and then delete 80. That makes us done. So here's what that would look like, and it basically allows us to promote 75. Last but not least, it has a non-empty right and subtree. So again, we go back to our original tree, and suppose we want to delete 50 from that. Well, 50's got a left subtree and a right subtree. What we need to do is we need to reduce this to either case 2 or 3. So suppose we go with no right subtree. That's case 3 that we just did. We need to find the immediate predecessor of this value, 48. So 48 is the immediate predecessor of 50. So we take 48 and we move it to where 30 is. And then we move it to where 50 is, and then delete the node that contains 50. Sorry, I was working on 30 there. So we find its immediate predecessor, swap it, and then we update the tree. So what it looks like here is we take that 50, we move 48 into that value, and then update that. It also does, we also need a little bit of house cleaning with making 45 the right child of 40. So that cleans up case number 4. That's the trickiest case, and you can see that if you look at the code from the leaked textbook. The other thing we might want to do is look at non-recursive traversal of trees. Now, basically the algorithms that we had in order, pre-order, and post-order, the ones that I gave you in the last presentation were all recursive. It makes them pretty easy to implement, but you're again relying on the system stack, and you may want to have your own stack for those. So we can write a non-recursive version of all of these. So for in-order traversal, we visit the left link, then or left subtree, the node, and the right subtree. And basically, we start at the root and follow left link until it becomes null. We then back up to the parent node, visit it, and then move down to the right node. Because links only go in one direction, we need to save a pointer to the parent nodes to go back. And so this ends up with a last in, first out. So we need a pound include stack in order to make this work. For pre-order traversal, it's node followed by the left subtree followed by the right subtree. And as with in-order traversal, we need to save a pointer to the parent node before visiting left subtree in order to visit the right one later. So we kind of need to keep track of where we started. So, and this is a last in, first out. So we make use of a stack again, and we maintain that stack separately. So you can see why the recursive is probably the more desirable one to implement. Post order is even trickier because we have the left and right to visit before we visit the node. And basically here we're going to need two stacks, one for the left and one for the right. And we also have to indicate to the node whether left and right subtrees have been visited. So we need a pointer to the ancestor node and store an integer value 1 before moving to the left subtree and 2 before moving to the right subtree. And then we pop these values off the stack after visiting. So we actually need two stacks, and we need to store some additional information and a couple pointers. So, post order is a bit nasty to implement non-recursively, but you can do it. Finally, the last thing you can do is you can have a function as a parameter. And this is something we typically show you in 321, so you'll probably see this in the first couple weeks of 321 next term, but let's take a look at a preview of it here. So when we do these traversals, visiting a node may mean different things. So we might want to output a value, update the value in some way, get user input, do a running sum. Instead of writing one function for each one of those things, what if we used our generic traversal function and then passed it a function telling it what we wanted to do? So you can pass a function as a parameter to a function. In C++, a function name without parentheses is considered to be a pointer to the function. These are called function pointers. And so you can specify a function as a parameter to another function. So you specify the function type. In the first case here, we have void, followed by the name as a pointer, and then followed by the parameter type. So here we're passing a function, and then in the parameter, we're going to call it visit, but it could be a print, it could be a increment, it could be a decrement, it could be a update function to it. It could be pretty much anything. And then we have integers as our parameter type. The second one is the same, but we're using a template. So pretty nifty trick if you want to reuse code, and function pointers definitely promote code reuse. So we can now write an in-order traversal function to do any type of operation. The parameter visit is a function, and it specifies the action to be taken at each node. So in the example code in the textbook, we can print or update each node, and that's kind of a handy-dandy trick. Next time, we're going to take a look at graphs, which is another more advanced data structure, and I'll see you at that time.